Welcome. In geometry, finding the distance between 2 points is easy if the path is a straight line. But what happens when the path is a smooth, continuous curve? Today, we will use the power of calculus to derive a precise formula for measuring the length of any differentiable function along an interval. Calculating arc length is vital in many fields. Engineers use it to determine the material needed for bridge cables, while physicists use it to calculate the distance traveled by particles moving along curved trajectories. Understanding how to measure these paths is the first step toward mastering spatial analysis. Before we dive into calculus, let's recall the Pythagorean theorem. For any 2 points, the straight line distance is the square root of the sum of the squares of the horizontal and vertical changes. This fundamental geometric principle is the building block for our entire derivation. We also need the mean value theorem. It states that for a smooth curve, there is at least one point where the instantaneous slope equals the average slope over an interval. We will use this to replace vertical changes with derivatives later in our proof. To find the length of a curve, we start by approximating it. We divide the interval from A to B into small subintervals. By connecting these points with straight line segments, we create a polygonal path that mimics the shape of the original function. As we increase the number of segments and make each subinterval smaller, our approximation becomes more accurate. In the limit, as the width of these segments approaches 0, the sum of these straight lines will exactly equal the length of the smooth curve. Let's look at a single representative segment, which we will call delta Li. Using our distance formula, this segment is the square root of delta x squared plus delta y squared. This represents a tiny piece of the total length we are trying to find. We can manipulate this algebraically to bring it into a form suitable for integration. By factoring out delta x squared from inside the square root, we transform the expression into the square root of 1 plus the ratio of delta y to delta x squared, all multiplied by delta x. Now we apply the mean value theorem. The ratio delta y over delta x is simply the slope of the secant line, which is equal to the derivative f prime at some point within the interval. This allows us to express the length in terms of the function's rate of change. By summing all these individual segments from I equals 1 to n, we get a Riemann sum. This sum represents the total approximate length of the curve. As we have seen in basic integration, this structure is the precursor to a definite integral. Taking the limit as the number of segments goes to infinity, the Riemann sum transforms into a definite integral. This is the arc length formula. It tells us that the length is the integral from a to b of the square root of 1 plus the square of the derivative. Let's test this with a simple straight line. Consider f of x equals 2x from 0 to 3. We know from the distance formula that the length should be the square root of 3 squared plus 6 squared, which is the square root of 45. Using our new formula, the derivative is 2. Squaring it gives 4, so we integrate the square root of 5. The result is 3 times the square root of 5, which is exactly the square root of 45. The formula works perfectly for linear paths. Now let's try a curve, y equals x to the power of 3 halves. First, we find the derivative, which is 3 halves times x to the 1 half. We then square this derivative to get 9/4 x, which we plug into our arc length formula. This integral requires a simple u substitution. By letting u equal 1 plus 9/4 x, we can evaluate the integral from 0 to 4. The final result gives us the precise physical length of that parabolic arc, demonstrating the formula's utility for nonlinear functions. Sometimes it is easier to treat x as a function of y. If we have a curve defined as x equals g of y, the formula remains almost identical. We simply integrate with respect to y, using the derivative of g and the vertical bounds of the curve. A critical requirement for this formula is that the derivative must be continuous. If a curve has a sharp corner or a cusp, the derivative is undefined at that point. In such cases, we must split the integral into separate pieces at the point of non-differentiability. Another edge case occurs when the curve has a vertical tangent. At these points, the derivative becomes infinite, making the integral improper. To solve this, we can either switch the variables to integrate along the y-axis or use limits to evaluate the improper integral. It is important to note that many arc-length integrals are very difficult or impossible to solve using standard elementary functions. In real-world engineering, We often use numerical integration methods, like Simpson's rule, to approximate the value of these integrals. One of the most common errors is forgetting to square the derivative inside the square root. Remember, this formula is derived from the Pythagorean theorem, where the hypotenuse depends on the squares of the sides. Always double-check your exponents. Another frequent mistake is using the wrong bounds. If you are integrating with respect to x, your limits must be the x-coordinates. If you switch to a dy integral, you must update your limits to the corresponding y-coordinates of the start and end points. Be careful with algebra. You cannot simplify the square root of a sum by taking the square root of each term individually. The square root of 1 plus the derivative squared must stay as a single unit unless you can factor it into a perfect square. To summarize, finding arc length follows a consistent 5-step process: find the derivative, square it, add 1, take the square root, and integrate. This systematic approach ensures you capture the total distance along any smooth path. The arc length formula is a beautiful bridge between geometry and calculus. It allows us to linearize a curve infinitesimally and sum those tiny lengths into a whole. Whether you are working in 2D or 3D, this logic remains the foundation of path measurement. Let's test your understanding. How would you set up the integral for the length of the sine curve from 0 to pi? Remember to find the derivative first. The correct answer is B, as the derivative of sine is cosine. Thank you for learning with us. Generated by Vision Solve AI.